Thank you, Aisling. Hi, everyone. I'm Phoebe, and I'm the other co-organizer of Newnham Speaker Series this year. And as ever, it's always strange when we gather on Zoom, but it means that we can reach more people that way. And it looks like we've got a really big, good turnout tonight. So welcome, everyone, to today's seminar. And we'd like to thank you for attending, and we express our appreciation to our speaker, Dr. Tina Potter, for taking your time to join us today. Dr. Potter completed an undergraduate degree in physics and then a PhD in particle physics at the Royal Holloway University of London. She has been a member of the Atlas Collaboration, one of the experiments collecting data from the Large Hadron Collider at CERN in Geneva, since the start of her PhD in 2005. After 6 years at the University of Sussex as a postdoctoral research associate, Dr. Potter joined Cambridge and Newnham as an early careers fellow in 2015. In 2018, she was made lecturer by the physics department, and in 2020, she was promoted to reader. She is currently a college lecturer in physics and in mathematics for natural sciences. Dr. Potter will shortly receive the Teaching Pilkington Prize for 2021 for excellent teaching at Cambridge, which we would like to congratulate her for this brilliant achievement. And today, Tina will introduce us to her research and academic experience. In her talk, which is going to be the first part of the session, Tina will discuss Seeing the Invisible, the Dark Matter Puzzle. If you have any questions, please ask them at the end, and that will be made up of kind of two parts, a question session about the lecture, and then we'll move on to Dr. Potter's academic experience and experience at Newnham as well. So please, Tina, the floor is yours.
Okay, thank you very much for that lovely introduction, and it does remind me how long I've really been doing this, and also that maybe I'm not as young as I used to be. Okay, but it is my absolute pleasure today to tell you about my area of physics. And what I'm really trying to do here is solve what we call the dark matter puzzle. And dark matter, and I'll explain this a bit, but it's completely invisible to us, and we're trying to see the invisible, and it's a real massive challenge. So I'll show you why and how we do this. So yes, who am I? First, I was raised in Croydon before I started off on my studies over to Royal Holloway to do an undergraduate in physics. I was absolutely set on doing astronomy until I started learning about particle physics, and it completely grabbed me, and I went down that road instead and continued there to do a PhD on the Atlas experiment. Actually, before we turned on and started on, I was there prepping the groundwork to see about the physics potential of our experiment. And then when I finished my PhD, I was dragged off down to Sussex with my old supervisor to start a new group down there, which was extremely hard and tough, but I'm very proud of what we built and achieved there. And in that time, life completely changed, and got my first dog, and then our second dog, and I had my first child. So it went from quite a quiet, very academic life to a life of almost absolute chaos, but I love it. And then at the end of my maternity leave, I saw an advert for early careers temporary lectureship at Cambridge, and I thought, well, what the hell, I'll apply, and I got it, to my surprise, which has been an amazing adventure. And then when I was here, we had our second child, and then I managed, when I came back from that maternity leave, to secure a permanent lectureship here. So it's been a bit of a whirlwind with life changing and things like that, but I'm very much hoping this year, one, we get out of this pandemic and start to socialize and everything again. And I'm really hoping to actually get just one more dog. Maybe just I'll convince everybody if we could do that. Okay, so let's get into the physics. What is high energy physics? So very, very simply, we are trying to understand the very fundamental building blocks of the universe, the fundamental particles in the universe, and how they interact with those very simple forces. So to break everything down, it is quite simple. There are only 12 mass particles in the universe. One you might be very familiar with, our electron. They're on the outside ring here. You might be familiar with the electron. That's the thing that's moving around with electricity. And it's got a heavier version called the muon and an even heavier version called the tau. You may have heard of the neutrinos in the universe, from neutrinos traveling faster than the speed of light, apparently, a few years ago. And then you may have heard about quarks, another exotically named type of particle. And we've got 6 types of quarks. 2 of them, the up and the down, both bind together to form protons and neutrons, the things that are in the center of atoms. So out of all these building blocks, we've only got a few of them that are stable, that make up everything around you today and the rest of the universe, and a few that are unstable, that used to exist back in the very early universe. And so these all interact with one another via 3 fundamental forces. You might be very familiar with the electromagnetic force and the photon. That's how we see. So that's the electromagnetic force. We've got the strong force, and it is incredibly strong. And this is mediated by the gluon. So these quarks are basically bound together as protons and neutrons via the strong force, by the exchange of something called a gluon. And then finally, we've got the weak force, and it's very well named. It is a very weak force. And this is responsible for things like radioactive decay. And this is mediated by the W and Z bosons. So we've got these 4 bosons here, responsible for the fundamental forces. And then finally, the new kid on the block is the Higgs boson there at the center. And this is responsible for some of these particles having mass. So this is a really quite neat puzzle that we have completed here, and it seems very straightforward, but we should always ask the question, is it really this straightforward? And we've got lots and lots of questions about it. So taking what we know about the standard model, can we explain our universe right now? So all these particles and the forces make up what we call the standard model in particle physics, and we stole that from astronomy, but that's fine. So let's have a look. Why do we study particle physics and high energy physics? So if we were in a 14 billion-year-old universe around here, looking out at our galaxies and other planets and everything today, but if we try and rewind our universe back in time, we get to the good old Big Bang. And if we take our physics back in time to the very early high energy universe, our mathematics starts to break down. And it starts to break down for very good reason, in that we think we're missing a piece of the puzzle here. So what we try and do experimentally then is to try and understand the physics of what was happening in the very early universe, and try and fill in the pieces of the puzzle so that we can extrapolate back to the very early universe quite accurately. At the moment, things start to break down, and we think we know that there are missing pieces of information here. So what we're trying to do is understand the very early universe by looking at very high energy physics. And we've got some big questions in my field of physics, and they are quite they really boil down to, what is the universe made of, and how did we get here? So we want to know what this dark matter in the universe is. When we have a look at the universe, we see that only about 4 or 5% of it can be explained by the standard model particles that we know about. About 26% of it is something called dark matter, in that it's massive, but it can't be explained by any of our particles that we know about. And then about another 68% of it is something called dark energy, which is responsible for the expansion of the universe, the acceleration of the universe. We don't really know what that is either. And we know dark matter exists. There's this very famous bullet cluster here, where we've got 2 galaxies passing through, galaxy clusters passing through one another, and it's done in 2 colors here. We looked at this with X-rays so that we could see really the luminous matter, the standard model particles that we know about, and that's in pink. And so as these galaxy clusters passed through each other, the pink matter there interacted with each other, slowed down a little bit as it interacted with the matter from the other universe. But the blue is from gravitational lensing, and that's telling us where the bulk of our matter is. And it seems actually that the bulk of the matter from these 2 galaxy clusters pass through without interacting with each other at all. This is again another smoking gun of dark matter. We would like to know what the difference between matter and its antimatter is. We've labeled what's left over in our universe. We've given it the label of matter, but it has every particle has an antiparticle in our standard model. They were produced in equal amounts in the Big Bang, and for some reason there's some small tiny difference which has caused the antimatter, probably so labeled it, to disappear and leave us with just matter. So why on earth are we here at all? We want to know what's what's causing that difference between matter and antimatter. We'd like to know if there's any structure in the flavor sector. There's some signs, and I'll talk about this later, of lepton non-universality, as some things being a little bit further away than what we expected. We'd like to know why the Higgs mass is so low, this newly discovered boson, which we're all very proud of, but it's a bit hard to actually bring it down to the mass that we've discovered it at. We actually would naturally expect it to be at a much higher mass, so that's quite interesting. And then we'd like to, hopefully one day, have some grand unified theory where all of our forces actually sit under the same umbrella and can be described by a single force. We'd like to unify them up in the early universe or very high energy. And then, this is a little bit embarrassing, but the best known force, gravity, is completely missing from high energy physics. We haven't described it at all. So there's 4 fundamental forces of the universe, but in high energy physics at the moment we're completely ignoring gravity. It doesn't really at the moment play a part unless you're at the very, very, very smallest scales or very, very early universe. So we can neglect it for now, but we would like to include it one day. All right, so what is dark matter and how do we know it's out there? So I've got this picture here of a galaxy, and galaxies rotate, and they rotate according to how much mass they have. And so as you go from the center of a galaxy out to the edges of the galaxy, the speed of rotation should slow down. However, when we compare our calculations of what we expect based on the matter that we can see using telescopes, for example, this luminous matter from stars and gas clouds and nebulae and stuff like that, it doesn't quite match with the actual rotation that we see. So what we expect is that the speed should decrease as we go further away from the center. What we see is very different. Actually, it's increasing and sort of more leveling off. So this was a massive surprise. If the matter, if the stars, for example, in the outer parts of these galaxies are actually traveling that fast, they should be flung out from the galaxy. It's a bit like being on a roundabout and it going far too fast. You'll get flung off. There has to be something holding the stars and all the matter into the galaxy. And we think that that is a gravitational force. So that's coming from essentially extra mass in these galaxies that we cannot see visibly, something that's dark. So we see this from the galaxy rotation curves, and we also see this when we make measurements of the very ancient light from the very early universe called the cosmic microwave background. If you turn on an old television, the static that you see is actually from this light from the very early universe. And we can measure that very accurately, and some small deviations or changes that we see across that power spectrum for that light suggests that actually we're in a majorly dark universe. It tells us that sort of the shape of the geometry of our universe. It also tells us that only 5% of our universe are the particles in the standard model that we know of. 26% of it is some other matter that we don't have any clue about, but it can't be explained by what we know. And about 68–69% of it is dark energy. So this dark matter is really a really big thing to me. I would really like to provide some kind of explanation for it. Our standard model particles do not. Either our particles are charged, which means we should be able to see them with photons, or they are unstable, like the bosons we have in the standard model, like the gluons and the W and Z bosons, or they're neutrinos, which are actually a semi-good, a pretty good candidate for dark matter, but because they're so light, they travel too fast, they're quite relativistic, and they would literally just sort of wash out and smear the whole structure of the universe that we see. So they're not a good candidate by themselves. So we do know that dark matter has to be something that's stable on the timescale of our universe. It's electrically neutral so that we can't see it with photons. It's heavy, it's got to be massive to provide the mass that we're sort of missing here. And it's got to be very, very, very weakly interacting. And that makes it pretty invisible to us. So really, it's just these gravitational effects that we're seeing, and we're trying to figure out what's causing it. So how do we try and see this very ghostly dark matter? We can either break it, shake it, or make it. So if we break it, we're looking for the dark matter particles in the universe themselves annihilating and producing maybe things like high energy photons. That's called indirect detection. So we're trying to break the two dark matter candidates into standard model particles. We could shake it. So this is direct detection where, I mean, we live in a galaxy. The Earth and the solar system is traveling through our galaxy, therefore we should be surrounded by dark matter. And as the Earth travels through this, we are basically traveling through a dark matter wind. And we hope that we one day will see one of these very, very, very rare interactions of a dark matter particle hitting one of our standard model particles and us seeing that sort of shake. But I work on the make it. So what I'm trying to do is I'm trying to take standard model particles, smash them together and make dark matter particles out of them. So this is what I do at the Large Hadron Collider, and I use the Atlas detector to try and see what's come out of it. We really smash together protons, and those are some of the small constituents inside of protons. And out of those collisions, I hope to make dark matter particles. These are the ones in red here. So to do this make it part of the dark matter puzzle, what we've done is a huge international effort has come together to build one of the world's best experiments, in my view. Just outside of Geneva, there is the CERN lab. And underground, about 100 meters underground, we have a 17-mile circumference ring. And to try and get that into your head, it's around the same circumference as the A14, A11 sort of loop around Cambridge. So it's absolutely massive. You're not going to be walking around those tunnels. Everybody gets on bikes. So it's all underground, and around these tunnels, you can see a picture of inside the tunnel here. We have these amazing superconducting magnets to bend the protons in a circular path. And we also have radio frequency cavities, which basically accelerate these protons to really, really high speeds or high energies. And we send them round, speeding them up at almost the speed of light. And then we smash them together and we see if anything interesting comes out. We don't just do it once, we do this billions and billions of times a second. We really do like to repeat our experiment here. The chances of creating something like dark matter we know would be very, very small because they're very weakly interacting. So if we want to see a handful of these special things, or even a couple of hundred candidates in these collisions, then we really need to do this many times over. So this is a little sort of reconstructed picture of what comes out of these collisions. You can imagine that one of the proton beams is coming in here and another is coming in here. The protons interact, something amazing happens according to the laws of physics, and then lots of interesting things fly out, and it's our job to really reconstruct what happened in that collision. So this is a really amazing piece of, this is a really amazing experiment, really. There's nothing like it in the history of mankind, and it's incredibly successful as well. We've got people from all over the world collaborating together to make this happen over many different decades. We've got particle physicists like myself looking at the data and trying to calculate the physics processes that are happening. We've got engineers actually building this amazing giant machine and the detectors as well. And we've got accelerator scientists making sure that we can really accelerate these protons and really deliver those collisions that are important to see the physics. Now, it's as simple as taking hydrogen from a gas bottle, stripping off the electrons on the outside, leaving us just that proton in the middle. And then we gather those together in bunches and start sending them around our accelerator complex in bunches of protons, and then training them all up together, and then colliding them at 4 points around the ring. And we've got these 4 amazing experiments here. We've got 2 very general purpose experiments, CMS, and then my experiment Atlas, which is the better one, but you know, we like to share. We've got 2 very general purpose experiments, and their goals are to really confirm the standard model is correct at these higher energy collisions that we're looking at, discover the Higgs boson, fantastic, we've already seen that, and then look for anything new, any new forces or particles or symmetries in nature, and to produce hopefully dark matter and see that signature too. So we've got these 2 very general purpose experiments, and we've also got 2 specialized experiments. One of these is LHCb, and I will comment a little bit on some fantastic new results from there. And they are looking at the same collisions as us, but really focusing on making some very precise measurements of the standard model, some very rare processes in the standard model they're trying to measure to very high precision to see if there's any deviation away from what we expected. And that's a very different kind of experiment, and as you'll see, they produce some interesting results already. And then over here at the bottom, we've got Alice, and Alice is another specialized experiment. Sometimes we don't just collide protons, sometimes we collide lead ions, which are even more massive. And Alice's main task is really to have a look at the strong force and how gluons and quarks form a plasma and interact over large distances. So quite a different goal set from the rest of the experiments here. Now, the way this works, because we're a circular collider, is when the beams are running, all 4 experiments receive collisions at the same time. The beams are basically just crossed over at each of the experiments at the same time. So we're basically sharing beam time. And as a particle physicist of the Atlas experiment, I have access to all of the data, as do all of my collaborators. So it's different to you know, these large telescope experiments. This is really shared beam time and shared data. I don't have a portion of the data that belongs to me. It's for everybody in our collaboration. And eventually we release it actually to the rest of the world. Okay, so this is a very, very long-term experiment. Just its sheer physical scale of the number of people involved means that we do this over multiple different decades. So this was sort of thought up of and designed and pushed for in the 80s and 90s. And we turned it on back in 2011 at lower energy than planned, because we needed to get used to using our machine. We took a small amount of data at that lower energy, and you know, I think after just 1.5 years of running, we already discovered the Higgs boson in 2012, which was an amazing thing to turn this huge experiment on and to have that discovery so quickly. It's really a testament to all the hard work that came before 2012. And then we turned on again in 2015, slightly higher energy, what we call 13 TeV, which is just a little bit shy of the design energy. So the protons were boosted to even higher and higher energies to achieve this, giving us access to hopefully more massive particles. And we ran that for about 3.5 years before we shut down again, and we need to sort of go in and tinker with our detectors, let's say, and tinker with a few things and upgrade it and make sure it's running smoothly. And we should be turning on again next year. I'd love to say we should be turning on in 2021. We're a little bit delayed because of COVID, as is everybody. And we're hoping to take even more data, maybe twice as much data set as we have previously, where I'm really hoping that we'll be able to see a physics discovery, not just hints of something new, a real physics discovery, which would be fantastic. And then even after that, we're going to upgrade things even further and take data even faster. So this has been a very long-term experiment. It's been the focus for about 20 years in high energy physics, and it's going to be running at least till 2035. So this is the Atlas detector. This is my detector. It's underground, 100 meters underground, in a massive cavern. And then we've got the proton beams come in through pipes there, and then in the other end there. You might be able to try and understand the scale of this if you can see these little people standing on a part of it there. It's basically the size of a 5-story building or a cathedral. It's absolutely massive and absolutely fantastic. It's filled with some of the best technology for trying to track and measure and identify the particles that fly out of the collisions. So the collisions sort of happen in the middle here, they come through the beam pipes, and then the particles that are produced in those collisions fly out and spray through our detectors. And we've got lots of different specialized layers. I won't get into the details of them here, but they allow us to really identify different types of particle from one another and measure their energy and momentum, and allow us to really reconstruct a picture of what might have happened in the collision itself that we can't directly see. So this is a sort of zoom in of what actually is happening inside the detector. So because we're colliding sort of clouds of protons, like bunches of them, what happens is as they pass through one another, we don't just have one proton pair interacting at the same time. For this example I've given here, we've actually got 11 collisions happening at exactly the same time. So there's lots and lots of particles traveling through, and it's an incredibly busy environment. So we've got these huge software and computing challenges. The Atlas detector has about 100 million channels. So think about it like 100 million wires connected to our actual detector that need to be read out. You need to read out their signals and understand what they're saying. And also we're colliding the protons 40 million times a second. So it's kind of mind-boggling that we've got a lot of data to record, and actually we've got too much data to record. Technology doesn't allow us to record this much data so quickly. So what we do is we have a really fantastic fast triggering system to try and decide whether we should keep the data from a collision or not, if it's interesting or if it's one of the many sort of mundane standard model events. And so it makes that triggering system makes a decision in less than a second, bringing that rate down to about 300 events per second to write to disk. So we really do, unfortunately, we don't keep everything that the LHC even does. But even so, between the experiments, we've got about 200 petabytes of data stored around the world, and that's just increasing as we continue to take data with the LHC. So to deal with that, we actually pushed for a distributed data system across the world, using massive data centers and supercomputers around the world to store and analyze our data. And that's now been adopted by and pushed even further by companies like Amazon and Apple with the cloud. So you can think about high energy physics as maybe also the mother of the cloud that everybody uses now. So what are we trying to look for in these collisions? What on earth do we do with this? So one thing that I'm trying to look for is something called supersymmetry, and it goes quite nicely hand in hand with the dark matter problem. So there's lots and lots of symmetries in nature, things like symmetries in time, symmetries in space, and we can introduce another symmetry between two different types of particles in our standard model. There's these particles, our mass particles, our quarks and our leptons. We can introduce a symmetry between those types of particles and the force carrier particles. Now, this is quite a natural thing to do. It's actually one of the last space-time symmetries that we can do. And if we do that, it actually predicts that we more than double the particles that could be out there in our universe, which is really interesting. And that's always fun to do, to give yourself something new to look for. So we end up with basically these big sort of shadowy super partners of our quarks called squarks. Everything's got a great name in high energy physics. And we've got partners of the gluon called the gluino, and then we've got more Higgs bosons to look for as well. And one thing that really has always grabbed me is that supersymmetry, if we have this symmetry in nature, it gives us a really fantastic dark matter candidate. One of the particles that's predicted is called a neutralino. We predict it to be stable, electrically neutral, very weakly interacting. It's a really fantastic dark matter candidate. Along with that, if that's not compelling enough, we also have quite a natural, I won't get to the technicalities, but way to describe why the Higgs boson could be as light as it is and not off at the highest energies and masses of the universe, and also gives us a nice way to unify the fundamental forces in our universe. So I'm really hoping that we're going to see supersymmetry at the LHC, because it does provide so many natural answers for me. So I'll try and break it down. What are we looking for? There's three main types of supersymmetry, I guess we can call it. There's the strongly produced SUSY, which is basically our squarks and our gluino. They should have the highest production rate at the LHC. And because of this, they should be quite easy to see as long as we can as long as they're within reach of the LHC energy-wise. And then we've got third generation SUSY. This is the stop and the spotum. And that's quite special because they look very like the standard model signatures. The LHC is basically a factory for producing top quarks. And so that kind of standard model background is quite high. If you're looking for stops and spotums, it's very hard to pick apart from that very large sort of factory background. And then my favorite is the electroweak SUSY, and it's all the rest of the particles, basically. It's our leptons and our charginos and neutralinos. Why are they my favorites? Because they have actually the lowest production rates at the LHC, which makes them rare and hard to find. And actually, if they're produced, they decay, and their signatures inside our detectors should be very standard model-like. So I really like a challenge. I'm trying to pick apart some of the hardest to discover supersymmetry from a very similar standard model background. Okay, so how do you start to look for supersymmetry? Now, unfortunately, supersymmetry, even though it's elegant and simple and just starts off with a simple symmetry between different types of particles, it actually has 125 free parameters roughly in, or 126 maybe, in this theory. And so it's really hard to sort of scan that kind of high dimensionality. So we try and simplify things, picking out particles and decay chains that we're interested in going off to search for. We've got to decide how we're going to produce new particles, maybe directly from the protons, or maybe they're going to come along with extra other particles that allow us to tag the event. We've got to decide what kind of decay we're going to look for. Are there going to be lots of SUSY particles in long decay chains, or are they going to go through our standard model particles and give us some kind of resonance and another thing to sort of tag the event with? And then we've got to decide what kind of particles we're going to go and look for: electrons or muons or taus or jets. What kind of particles are we going to have in our final state? And then finally, I'd love to say we could go off and just have a look for the dark matter candidates themselves, which you can see here. Unfortunately, by their very nature, they're completely invisible. And this is one of the only times I'm going to say something about CMS here, our sort of sister experiment across the ring, because they have a very nice event that shows an example of something called missing energy. So if our dark matter candidates are produced in, if we've got SUSY particles produced and it decays down to our completely invisible dark matter candidate and some other particles, what we would expect to see is an imbalance in the event. So all of the things that we can see, for example, maybe these electrons, we've reconstructed things going off in this direction, there's clearly sort of something missing over here. there's an imbalance. And this is a simple conservation of energy or conservation of momentum. So basic physics laws. We would expect a balance here. So what we think's happened, and you can see this with this pink arrow denoted here, is that something escaped detection and went off in this direction to balance the event. And this is called missing energy, and it's one of the smoking guns of supersymmetry or dark matter, really. Something invisible went off over here, causing a big major imbalance in the event. So we try and put this all together, as well as, you know, very precise background estimations and uncertainty controls. And I hope this usually all comes together into coherent search strategies across multiple channels, particle productions and decays, to a very coherent search strategy across as many different SUSY signals as we can. And I hope all of this together soon will bring us to some kind of, I won't say SUSY discovery, but really anything new will do for me. So where are we now? We don't have any signs of SUSY yet, I'm afraid. So Atlas and CMS are both sitting at the end of our second runs with quite a good amount of data, and we haven't seen in our SUSY searches or any other new physics searches any significant deviations from what we expected. That's not the end of the story, though, because that allows us to say what we know isn't there, and then tells us where we could still go and look. So, for example, if we take our strong SUSY searches for these squarks and gluinos, we can have a look at the masses of the squarks that could have been produced against the masses of the dark matter particles, and basically exclude everything underneath these contours here. I won't get too much into the details, but we've been able to exclude squarks and gluinos up to around 2 tera electron volts in mass, which is really quite high and quite stringent. It does depend on how they decay, though. So there are some holes and still some lots of uncovered space, depending on what kind of model you look at. Things are a little less stringent when you look at the third generation, just because they're very standard model-like here. We can exclude the stops and the spottoms up to around 1 tera electron volt in mass. And again, there are some holes where things get a little experimentally challenging to separate from the standard model background. And then finally, my favorite, this is what I've been working on for years, is the search for electroweak SUSY particles, these leptons, neutrinos, and charginos and neutralinos. Now, because the production rate is so low at the LHC, these are very rare things, even if they do exist in nature. The limits are far less stringent here. And depending on the particle, we can exclude the mass out to about 700 to 1,000 giga-electron volts. But we do have some rather large gaps in places. For example, for lepton production, there's this big gap, this big white gap here, all the way down to very low masses that we still haven't been able to cover, because it's very experimentally difficult to actually have sensitivity there. And it's one of the things that we're looking at, particularly with the recent results from other experiments. I'll move on just so I can get to this bit. So we haven't seen any evidence of SUSY, but hints of something are appearing from other areas in high energy physics. So I'm going to move to LHCb here, because we had an amazing updated result from LHCb, which continues a pattern actually that they've been seeing for the last few years, and also, I'm proud to say, is led by my colleague here at Cambridge. I mean, normally just down the corridor when we're in the same building. So this was led by Paula Alvarez-Cartel, who's here in Cambridge. So what we're trying to do here is test one of the fundamental assumptions of the standard model, that electrons and muons are treated the same by the fundamental forces. So we take a very rare decay of something called a B-meson, which is a bound state of an up and an anti-bottom quark. And these are unstable and they do decay, and they can decay to types of particles called kaons. Doing this through some complicated loops of other particles to a couple of leptons as well. Now, the standard model says that these should either be electrons and positrons, or muons and antimuons. And it should produce the electrons to the muons at exactly the same rate. That ratio should be 1. So this is an excellent way of trying to test one of the assumptions from the standard model in a very rare decay. We're looking to measure a very, very small value. And if there is something new, some new physics or some new phenomenology there, it should be quite easy to see a deviation from a small value. Plus, we understand the theoretical calculations, the predictions with this very, very well. They're very precise. So LHCb has gone away and done this, and whoa, wait, this ratio is less than 1. So this ratio for the production of muons to electrons in this decay should be about 1, or should be exactly 1 actually. But for the last few years, they've been measuring it away from 1. And as we've added more and more data from the early days they doubled their data almost there and almost doubled it again with this latest result, we're quite far away from 1. This is 0.85. And this is 3 standard deviations away from the value of 1. So this has sort of now hit a golden standard of 3 standard deviations where we say this is evidence of something new. It's very unlikely that this deviation will go away at this point. The gold standard to announce a discovery is 5 sigma, and that's what we were able to do with the Higgs boson. So we're hoping to add more data now and try and keep measuring this with more and more data to see if that significance about how far away it is from 1 really increases. Now, it's not just seen in this one decay mode here, it's seen in multiple decay modes. This pattern that electrons and muons are being treated differently in the standard model is appearing in quite a few decay modes. So we think that this really might be the first glimpse of new particles affecting these very rare decays. New particles as something like a leptoquark, which is something that has been theorized to bind to both or interact with both quarks and leptons. If leptoquarks exist, we might say that we might be able to explain this by they are also appearing in this decay chain at a very, very low rate and affecting the rate of its decaying to muons versus electrons. So hopefully this is sort of just cracking the window where we're starting to see some anomalous behavior before we actually discover something in the main experiments. And then again, this has been a very busy start to the year. A few weeks ago came the results of the G-2 experiment. So this, I mean, it's been quite a, we've been waiting for this result for about 20 years now after this was measured to be anomalous about 20 years ago, but we really needed another experiment to try and verify this. So let me try and explain what this is. So muons are charged particles and they have something called spin, which means they're going to act like little bar magnets. And if you put them in a magnetic field, they're going to feel a force and they're going to start to basically precess around the magnetic field line. You can think a bit like a spinning top. I've got a picture of it here. So these muons, because they're charged and they have spin, basically precess around the magnetic field, but the rate that they precess around, that frequency, is completely determined by the interaction of the muon with the magnetic field. Basically, the muon is exchanging photons with the magnetic field. It's as simple as that. So our poor little muon, living for a very short time, exchanges photons. And we can describe this with these very simple diagrams. For example, it can exchange a photon, and there can be lots of other particles in this exchange as well. We actually need to, if we want to calculate this to the highest precision, we actually need to include all of the known standard model particles here. So our diagrams become more and more complicated the more accurately we need to calculate this. But, you know, even though these more complicated ones, for example, here, they're not just a simple photon exchange, they are important because they will have a very, very tiny effect on this muon precession frequency. So this is something that the muon G-2 experiment has measured incredibly precisely. And the precision is absolutely amazing. It's 0.46 parts per million. So this is one of the most precise measurements that we actually have in physics. And the anomaly 20 years ago was from the BNL experiment, the G-2 measurement. It was, if I try and remember this, about three standard deviations away from the standard model prediction. The new Fermilab or G-2 experiment here completely agrees with that. And since they're independent experiments, we can actually combine those results together. And the experimental average is over 4 standard deviations away from where we expected it to be. So this is absolutely fantastic. And again, it's evidence of something new. I think, and this is all we're sort of talking about at the moment in the Atlas Susie conversation, is what could this be? If this is supersymmetry, what could be causing things like this? And we think actually it would be quite naturally explained by the superpartners to the muons, so-called smuons. So this is very much in the camp of electroweak supersymmetry with very low production rates, and so again, rare and difficult to see. So what we could have are smuons being actually involved in these very rare diagrams when the muon is exchanging a photon with the magnetic field. And that would change the precession frequency of the muon's magnetic moment. And so we do search for smuons and other leptons in the Atlas experiment, but there was that great big gap that I pointed out earlier. And it's very much uncovered and still in play. So it's very important, I think, at this point for the Atlas and CMS experiments to go and try and fill this gap. It would be this anomaly and also the LHCb result would be naturally explained by smuons existing in the universe if they had masses sort of less than 1,000 GeV, so a little bit off this chart. So there's a lot of uncovered area right now that's still in play, and this is a very exciting time, and it's really pushing us to try and push our sensitivity out to those places and really see if it's there. So what's next? Right, we're going to turn on, take far more data than we've had before, hopefully see those smuons or whatever it is that's causing it. And hopefully these things that are causing the G-2 results and the LHCb results is something that's within reach of the energy of the LHC. If it's not, we might need to look a little bit further. So at the end of the LHC, we're going to turn on and collide things even faster and take even more data, but we're not going to increase in energy. I hope when we take that last big set of data, actually, we will be characterizing something new. We would have seen it and produced it. But we could be sitting there at the end and need a little bit more energy or need a more precise experiment. So it does depend if we're sort of in discovery mode and measuring that new physics, or in search mode, and maybe we need more statistics or higher energy. And there's quite a few things that are on the table right now for future colliders, and we really need to start planning these and starting to build and push the technology now, because they take decades to do. So there's an idea for a very precise linear collider. So the LHC just outside Geneva is here in this white circle here, but to have a very linear collider instead, to basically give us a Higgs factory and do lots and lots of Higgs physics, but then also increase the energy, which actually means increasing the length of this thing from the first phase, which is in pink, out to green, and then out to blue. So this thing is absolutely huge, to really increase the energy and see if we can make something new there. Or my favorite right now, and something that I'm working on, is to take the LHC and build the next generation circular collider off of it. So the LHC would feed into a 100-kilometer long tunnel outside of Geneva. And this is a massive engineering challenge to actually even dig that tunnel. So it would have a few phases. We would start off just colliding electrons and positrons to have a precision factory and do all of our Higgs physics as well. And then this would lead up over a few decades to a proton-proton collider. So basically an epic LHC, essentially. This is the future circular collider that we would like to have there. And it would be colliding protons at energies 7 times higher than we are doing right now with the LHC, and really allow us access to much heavier particles. So if there is something, if there are these new particles and they might be just outside of the LHC's energy reach, i.e. basically on the shelf above, the future circular collider could really reach that and let us know for sure. Okay, so I'll finish there. So I'm really proud of the LHC and the experiments that come along with it. So this is the biggest experiment that we've done in all of human history. We have this massive, huge scale experiment, and we're probing the most tiniest things in the universe. And we've got this collaboration, this international collaboration, that we share the knowledge, and we push the technology for all the technology that we produce is given back freely to the world. So I've got some very high hopes of discovery at the LHC, even more so since the sort of little glimmers of hope that we've been given this year already. And I hope to find some explanation for our dark matter in the universe. I think it could be electroweak Susie. I'm even more hopeful now, given these latest results, but it is really difficult to find. I love a challenge though, and I think if we dig deep into the data, hopefully we're going to find something. But we've got to look forward to the next generation of colliders. They take a very long time to build, sort of even beyond my career, actually, if we're looking at the future circular collider. This literally means more digging into the ground, any way you look at it, but it should at least let us measure the new physics properties, that any new physics that we see at the LHC. And if we haven't seen it already, then we'll be continuing that quest for the dark matter and also measuring the standard model more and more precisely. Okay, and that's it. Thank you.
Wonderful. Thank you so much, Tina, for that very exciting and accessible as well talk. And we feel very honoured to have your time today as well. So maybe, I don't know if you want to keep, for the moment, maybe keep the slides up, because we'll open the floor up for questions. And if anyone has a question they'd like to ask Tina, just either submit it to the chat or raise your hand. I believe that's how it works. And then you can speak your question to Tina or pop it in the chat. And then following that, our lovely Julia will move into an interview section with Julia, where Julia will ask Tina some questions. Okay, so has anyone got any questions for Tina before Julia jumps in with hers? Okay, so I think Luis Fernandez, you have raised your hand.
Yeah.
You want to go for it?
Sure, thank you. Thank you very much, Tina, for the talk. It was pretty interesting, first of all.
Oh, thank you.
And I would like to ask a question regarding, could you put up the slide on the supersymmetry?
Yep, that one. Nope, that one.
Yeah, I wanted to ask, how come that from the force carriers, like if it's just a symmetry, how come that we get more particles in the supersymmetric part?
No, this is really interesting. So actually, in the standard model, the photon and the W and Z actually come from a mixture of fundamental fields. And this actually makes them somewhat related to each other and unifies the electromagnetic and weak forces. So when we do the symmetry, the supersymmetry, it's those super fields which have partners, and then they start to mix together. And what we find is that along with an extended Higgs sector, we end up with more particles. So it's partly due to the mixing of the superfields, and also partly due to the fact that we need more Higgs particles.
Okay.
I hope that somewhat helps. So yes, they're mixtures of the superfields of Winos, Binos, and Higgsinos.
Right. Okay. Thank you so much.
Thank you, Lewis. Anyone else? Anyone else got a question for Tina? So Mina asks, why did it take 20 years for the, I'm going to butcher the pronunciation probably, muon G2 measurements?
Why did it take 20 years? Right. So when the old experiment at BNL shut down, there was a big drive to have another experiment, but where is it going to be done? BNL, for example, that site was going to move on to do house another experiment. They weren't quite expecting this anomalous result. And so Fermilab down in close to Chicago took up the mantle of this, and a lot had to be done. You need to literally build this amazing magnet system that they have here, and also the very precise readout systems and the experiment itself, and that can take a few years. They actually transported this magnet ring down from New York State, actually down to Illinois, so that took a long time. And also perfecting the technology so one of the things that's very important to get right in this experiment is understanding the magnetic field that you're applying to your muons. And so understanding the uniformity of that magnetic field is very, very difficult as well. And getting that right. And then I would say, finally, muons are very difficult beasts. They're sort of every day. They're produced as part of cosmic ray showers all the time in our atmosphere, but they are short-lived. If you can make them move very quickly, you can use relativity to actually make them live quite long in the lab. So again, you've got to understand how to keep your muon beam alive for as long as possible. So that usually means high energies, as well as a very, very uniform and accurate magnetic field. So that takes time. And then, of course, once you've built that all up, all of that technology, you need to run for a while as well. And then do your data analysis. So yes, it takes a while.
Thank you, Mina, for that question, and thank you, Tina, for that answer. Any more questions? Yeah, you want to go? Do you want to unmute?
Yes, of course. Thank you very much, Tina. Lovely talk. I did the opposite as you did. I started off in particle physics and went to astronomy.
I was going to say, I think I recognize the background.
Oh yeah, I mean the IOA. Yeah, so my question is, so when we built the LHC, we sort of knew already that we would find the Higgs particle, or at least we had very strong hints of it. But going further into the future, do you think that we have equally strong hints of new physics to justify building such a very expensive experiment as like the future, the huge particle accelerators you were talking about?
It's hard. The Future Circular Collider, the hadron physics that I personally would be interested in definitely comes after I think I would have retired. So I'm never talking about this in terms of me, but if we haven't seen anything else at the end of the LHC, we do have to ask ourselves very seriously if the FCC is worth it. And I think it's worth it as part of a long program of physics. So if we can first give ourselves our precision Higgs factory out of it, then yes, then we've got our tunnel for starters. Once you've got your tunnel, it's quite easy to upgrade it. So this would be like the jump from LEP to the LHC. And we could upgrade it with hopefully the magnet technology that's moved on to a Hadron Collider. I would say probably the Hadron Collider is very hard to justify right now by itself. And I would very much hope that we, at the end of the LHC, will be in a much better position and will know exactly where we should be looking. I hope, I mean, we could also be sitting in a discovery mode where we've seen new physics at the LHC, but it's not something that we can do with an E+ E- collider. And then we do need a new Hadron Collider. So I think we need to plan for this, understand what the technological challenges are and what such a large ring can offer us in between now and then. So yeah, I think it's worth it. But all this conversation happened about the LHC as well, of course. So
yeah, true. And also maybe if you know, you said that all the knowledge generated is giving back to the public, basically. Do you know the economics of that? Like, how worth is it to invest in this type of science?
no,
This is something I thought of.
I think, okay, there was a number I heard the other day. Generally for science, you know, you get more back for the pound than you put in. I don't know what this would be for high energy physics itself. I mean, it's so far reaching, things like Wi-Fi, things like even monitoring the gases for anesthesiologists during operations, to even sort of rebuilding retinas and things like that. It's so far reaching. I don't think a pound sign has actually been put on it.
Okay.
But it's,
and the internet itself.
Yes. Although the instrument itself doesn't give back directly, but the technology does. For example, all the accelerator technology is used for things like proton therapies in hospitals, for starters, and it's hard to put monetary value on things like that.
True, true. I also said the internet itself we got from CERN. So
yes, I mean, we've either ruined people's lives or made them better.
Thank you very much for your answers.
You're welcome.
Lovely. So perhaps we should just move in so we don't take up too much time, Julia, into your interview, into your questions. And if anyone does have any more questions that they'd like to ask Tina, then pop them in the chat and then I can kind of throw them in as Julia goes along. So take it away.
Yeah, thank you very much, Tina. That was really, really interesting. So I think the first question that I wanted to ask you perhaps relates to your talk. So what do you think is the most exciting aspect of particle physics that everyone should know about?
Well, right now, I mean, maybe we take it for granted, but we really are sitting, I hope, well, I think it's sort of coming true, in a really fantastic era of discovery. So we've just discovered the Higgs boson, and maybe it's become a little old hat now, but that was being looked for 50 years before we found it in 2012. And now that we're starting to see some of these hints of something new, I find that really exciting. I can kind of, when I teach my course, there's a little analogy. Just before they discovered the Z boson, there were little hints of something new. And you know, the window was starting to open on the physics that was affected. I was starting to access it, and then they built a new machine and they discovered it directly. So I think we're actually sitting in an era where that window is starting to open, and we're starting to see some of these anomalies, for example, those lepton flavor anomalies from LHCb, and also these G-2 ones as well. I think these anomalies are going to grow. I think that's amazingly exciting. And then it's going to culminate in the discovery of something which is responsible for causing all of that. And that, I mean, I could hope that it's supersymmetry, but it would just be amazing to see something new and characterize it and find out what it is. So yeah, I think that's amazingly exciting.
Thank you very much. Yeah, I mean, something that I find sometimes tricky to tell my friends who are not necessarily from a STEM background is to just check the news and just read all of these very interesting scientific discoveries. But do you have any advice on how people may do that if they don't come from a STEM background? Because, for example, in the recent months, we've seen headlines such as evidence for a fifth nature, for a fifth force of nature, sorry. So how do you think perhaps people who don't have that much experience in the field should go about interpreting this news?
I think some news sites handle science issues differently from others. I think as long as you've got an interview with one of the members of the collaboration, it's usually absolutely fine. They've gone over things. I mean, it's the same in astrophysics and astronomy. I think the outreach is usually quite good and broad and widespread, and we do quite a good job of communicating our science. But of course, the details, if you're really interested in the details, they can be hard to access, because these are usually, you know, high precision experiments relying on understanding the minutiae of something very small and complicated. But you know, there's a lot of popular science books out there. There's a lot of articles that do try and break these things down. And I mean, after the G-2 and LHCb results, I mean, YouTube is just flooded with fantastic explanations and talks about how this is done and what it really means. So I think the information is there at their fingertips. It's really, as with all news things, is the quality of the source.
Okay, thank you very much. And relating to your experience in Atlas and in CERN, because you've been part of the Atlas experiments since you started your PhD, what do you think are the advantages of being in such a large collaboration, and perhaps related to the disadvantages?
Okay, well, I'll start with the advantages. So if any of you have ever been to CERN, you may have experienced this. It's a very different community, I think, to the rest of science. There's the real feeling of collaboration and this real free exchange of ideas without worrying that you're going to be robbed of some discovery, because you're all working together. It's an incredibly enriching environment to work in. When I go to CERN, I talk with people, we bounce around some ideas, and then there's a fruit there, and we go away and we do something, and it's very exciting. And there's so many fantastic people to work with, and I cannot underline that enough. I mean, in Atlas, there's about 10,000 people, and you know, going along all kinds of walks of life, and there's a large subset of them which I just adore working with. So yeah, I mean, it's really just the scale of it, the excitement of it, and I don't think that we can do science on this kind of scale without this sort of matching army of enthusiastic scientists. So it's an amazing environment to be part of. And you probably have something similar in astronomy with the very large scale experiments as well. Then, oh yes, disadvantages. That's what there are disadvantages, right? And I think this comes in part and parcel in working in any large collaboration, is that you need structure and organization and rules, and you need those to be really clear, and you need them to be effective. So as time goes on, I'm happy to have been part of this. Actually, we're refining these rules to better suit the working practices of our members, and also the science that we're trying to do. When we review things often and see how it works, and hopefully streamline things that are best for the time. Although it's really hard to get that right, which is why we review things frequently. And also, I mean, it can be laborious and a political process as well, and that can be tiring, but it's certainly a disadvantage. I'd love to remove that side of it. That would be fantastic, and just do the science. But on this kind of scale, it's just part and parcel of the structure. Okay,
thank you very much. I certainly agree that in the aspect when you're working with people who are passionate and really interesting, then it's a lot better. But yes, during your PhD experience, in general, how did you find it? And I guess being a part of a large collaboration at such an early stage, did you feel pressure to publish?
So in my PhD, for my PhD, I mean, I didn't feel it then, but this was sort of 2005 to 2009. We hadn't turned the LHC on, so we didn't have any data to publish yet. We were sort of just laying the groundwork really for the early physics studies that were going to be done. So I didn't feel any pressure to publish then, but when I started my postdoc, we turned on the LHC and the data flooded out. And I mean, it really flooded out. I don't think I've really experienced anything quite like this. So I felt a real urge to publish then, and this continues actually, this urge to publish. And it's not really an urge to publish to better my career. It's that this experiment is producing data. That data is sitting right there, and we need to look at it, and we need to share those results with the physics community. So it's kind of this sort of urgency of drowning in data as it keeps flooding in. I get a breath every time we have a short shutdown, but yeah, I feel a responsibility to get it out there. But yes, I'm just drowning in data. So in that sense, it's kind of easy to do.
Thank you. And sorry that I hadn't realized, but I think you're still sharing your screen. So please feel free to stop sharing at any time.
There we go.
Thank you. So broadly, how do you find the transition from being a PhD student to being a postdoc? And I don't know to which extent this really had an impact because of the LHC being turned on, but in general, how do you find it?
It was very different when we turned on. It was a very different lifestyle. Suddenly it was going from sort of feasibility studies and interesting things here and there to a real rush. There was so much to do, and everything sort of had to be done yesterday. And this is something we've all reviewed actually in sort of our analysis and publication processes now within Atlas, in that the pressure that we apply has to be sensible. There's no point always saying that it has to be public by yesterday if there's really no need, and taking an extra week to breathe and sleep and double check things. So that the lifestyle of the data flooding in, that was a really big change, and it did actually make me reconsider what I was doing, and luckily I think I stuck on the right path. But yeah, I didn't feel the career pressure to publish from that, just because I had so much to do.
Okay, thank you very much. And perhaps moving into the next stage of your life as an academic, and especially as a lecturer at the university, what do you find the most rewarding about teaching, and what are the aspects of lecturing and supervising at college that you think benefit you the most as a researcher and perhaps as a person?
For me, certainly as a postdoc, I found that I could be very, I could have almost tunnel vision with what I was doing, and not keeping an eye on the rest of physics. And lecturing really pushes you to not just to understand other areas of physics, but actually to be able to explain and describe them in many different ways to many different peoples. An incredible level of detail that's needed there. So it's really the students who have pushed me to do that. I mean, I've been teaching my course for quite a few years now, and even the other day, they're still asking questions that completely stump me. And I have to go away to the books, write out a few pages of things, and come back to be able to explain it to them clearly. So, I mean, I personally get a real buzz out of the interaction with students, those sort of wow moments that you can give them, clearing up things and linking to other areas of physics with what we're talking about. So I mean, I think that's what I really love, those kind of interactions, and then also seeing their success academically as they move on and do other things, you know, whether some of them stay on to do PhDs and postdocs in my field, which I love, but you know, even if they fly off and do something different, I take a bit of pride in their success. So that's what I find most rewarding, the students themselves.
And it has been recently announced that you will receive the Pilkington Prize for excellent teaching at Cambridge, as Phoebe was mentioning at the beginning of the talk. Congratulations. I was wondering, do you think there's anything specific apart from experience that makes you a good teacher or a good lecturer or a good supervisor?
Yeah, this was interesting. So the pandemic last year happened in the middle of teaching my course, and it really made me reconsider teaching itself. Like, in these situations, how can I convey the information to the students successfully, especially under the stress that they're under? What format should I use? What kind of chunks should I be giving it to them? And how can I still connect with students? You know, those chats at the end of lectures and before lectures and, you know, popping by my office were gone. And so how can I still give them a sort of positive and nourishing learning experience? So what I've been able to do, and also what I've been able to pass on to other people this year, is that a good lecture really just, you need to focus on that student experience. The physics and the facts that you're imparting sort of come with it, but what is that student experience going to be? What is the outcome that you're looking for? And also to be open to feedback and improvement. We've all got room for improvement. So in my views, you know, skills can be learned if you're open to listening, and experience can be gained, but the very first step is really just to care about what you're doing.
Thank you. I think this is really encouraging. And now I'm going to try to ask a few questions about your experience at Newnham, and maybe before Newnham. So during your whole experience in physics, as an undergraduate, as a PhD student, as a postdoc, as an academic, have you ever felt that you have been treated differently, and not necessarily in a detrimental way because you are a woman?
I'm really, really lucky, I think, to say no. And I think anybody who would treat me, you know, even detrimentally, they'd be crossing the wrong path, I think, there. But I'm sad to say that because I have a lot of colleagues internationally, I have seen them subject to sometimes just some shocking behavior, actually. That happens abroad and even sometimes in the UK as well. So I know it certainly goes on, but I am privileged not to actually have it happen to me, or notice maybe, but
Thank you. And perhaps due to these large collaborations, this is not such an issue I can expect in particle physics. But how do you think things have changed for women in STEM? And maybe you can speak about what you've spoken about with other academics at Newnham.
yeah, so one thing that we're seeing just sort of generally for women, and I would say this is actually beneficial to men as well, is that the playing field is sort of leveling for everybody. So workplaces, including Newnham and the department that I work for, they're far more, they're better at openly supporting staff who have, for example, care duties, either of older or younger family members, right? This goes all around. And then also in the same thing as guiding staff to and through career opportunities as they come up. That is really improving. And I think that's there for everybody, which is good to see. You know, this sort of expectation that people should be working 80-hour weeks and also be jetting off everywhere to speak to people all the time. That's the only way that leads to success. And that's completely crumbling away now, I think, as we're more open to supporting the fact that people are not simple beasts who sit in the lab and jet around everywhere. So yeah, things have, I think, really improved. But I would say that it's not just STEM. I would hope that more and more workplaces everywhere are actually being more open to this.
Thank you very much. And perhaps relating it again to what you mentioned at the beginning, that you originally applied to the position you got at Cambridge when you were on your first maternity leave. How as an academic, how do you learn how to maintain a healthy balance with your family and your health and your work, and how do you think this has changed for you over the years?
Yeah, I'll start off by saying I don't think there's really anything that you can define as a healthy balance. It's different for everybody. So it also changes. I mean, honestly, with my family, it changes from week to week. It's what they actually need. So I try and be flexible, and I go where the flow, where's needed. Is this, you know? So tonight's going to be my little work night, giving a talk to yourselves, and then tomorrow I'll just make sure I pick up the kids early and spend a bit more time with them. So you really need to just go where the flow is needed, allowing you to sort of put out fires. I'm really lucky, and I'll put my hands up. I have the support here at home to do that, and I have the support at work to do that, and it's absolutely invaluable. It doesn't always work. I get things wrong a lot, but I don't punish myself. I use it as a learning experience. But having the children has actually given me this perspective on things that I don't think I really had before. I wouldn't have probably applied for a Cambridge lectureship before. I would have considered it out of my reach, or just too daunting for me to really do. It's sort of, it makes you drop your guard a little bit. I've seen what I'm capable of. I find children far more challenging than my job, and I'm more ready to push outside of my comfort zone, if that even really exists anymore. But yeah, I think it does give you this perspective. It makes you think more clearly, and also be more flexible in as what you can actually attain.
Thank you very much. I think this is beautiful. Yeah, so taking it back to your experience at Newnham, what inspires you the most about being at Newnham, and what do you think Newnham has been able to give you as a woman in STEM?
So it's a very different place to the physics department, which is still male dominated, but getting a lot better. But yeah, when I go to Newnham, it's just a very different experience. You know, you walk in, you've got your beautiful, peaceful gardens, which always makes me sigh with relief. And also the people are just utterly divine, aren't they? I mean, I relax when I walk in. I look forward to my next conversation. You know, I don't know what my conversations are going to be like whenever I walk into Newnham. It could be about shoes, it could be about the garden, it could be about something completely off the political scale that I've got completely out of my depth in, or it could be about science as well. So I find that surprise of the conversation that I'm going to have really, really nice as well. But then I also love that the college supports the STEM subjects wholeheartedly, and also the success of the women that are there. And I really just want to be part of that story. Yeah.
Thank you very much. I think this was everything from me. So thank you. And
questions.
And I think that's just a really nice note to end on as well, to be honest, Tina, especially with this whole year celebrating women at Newnham and women in education as well. So thank you very much. And I just love the way you managed to weave together your research, your consideration of pedagogy and teaching, as well as your family life as well. It's very inspiring to see. Aisling, I don't know if you have something.
No, I was just coming to say I think that was a beautiful way to wrap things up, and thank you so much for your time. We really appreciated having you here. I know members of the MCR in particular, so thank you very much for your time.
Thank you very much for the opportunity. It was very nice.
And thank you everyone who tuned in today to watch the talk as well. And we'll be giving more talks over the coming weeks as we head into the Easter term as well. So I hope everyone has a restful evening and a lovely end of the week, and take care.
Bye, everybody.
Bye. Thank you very much.
I think.